Good morning, everyone. Welcome to our little session about hydrogen. You're all on mute just now. I have no idea what you're doing to the camera, but we do want your contribution, and we'll ask you to put some questions in the chat or the Q&A function later. And everything you contribute will be very helpful to us in our future hydrogen work. First of all, I'm your host for today. I'm John Devania. I'm a Senior Standards Manager at British Standards, and I'm responsible for the team that manages the UK energy-related committees, including most of those that have or might soon have some hydrogen-related work, extraction, refining, storage, blending, metering, and use. So to set the scene, the UK net zero policy is the main pillar of our commitment to meet our national obligations in tackling climate change. That hasn't changed with COP26. A key strand of the policy is the key part of the policy is a two-strand approach to the use of hydrogen as a low-carbon fuel. Our speaker today will outline trials that are underway to prove the viability of blending hydrogen in the existing gas network. And after that, we will discuss the issues that there are with making that work. Tommy Isaac is from Progressive Energy and is the project manager on the High Deploy project. So over to you, Tommy. What can we learn from the project?
Many thanks, John. I take it that you can hear me. Is that okay? Brilliant. So just everyone's awareness, I've got my camera off today just because I'm working remotely, so I haven't got my external camera, and the laptop camera has been well designed and put at the bottom of the screen, so you get a rather sort of attractive shot right up my nose. So I thought that might be slightly distracting, so best just to not have it on. My name is Tommy Isaac. I'm the head of hydrogen research at Progressive Energy, but my day job is the project management of High Deploy. As John outlined, this is the UK's blending programme, and what I'll do is go through the kind of progress that the project has made to date, and where we see blending really starting to materialise within the UK. So just to set the broadest scene that I can, the objective of the High Deploy programme is to be able to demonstrate primarily to the HSE that the transportation and utilisation of hydrogen blends with natural gas up to 20% hydrogen is a safe thing to do, and is as safe as natural gas today. And by being able to make that argument in a robust manner, we'll then be able to unlock the regulatory hurdle, which at the moment is prohibiting any hydrogen being transported within the gas distribution network. We are a 6-partner consortium funded through the Ofgem Innovation Programmes, which is called NIC. In total, we are we are formally two projects, but in reality, it is just one project, and the 6 partners are the same on both projects. Our 2 lead GDNs are Cadent and NGN. Us, Progressive Energy, who are the overall project managers, the Health and Safety Science Division, who lead on our technical side of things, Keele University, who hosted the first trial that I'll go into in a few slides' time, and ITM Power, who provided the electrolyzer that produced the hydrogen for the first trial. So to set the scene on what's the point of blending, so there's much discussion over the role that hydrogen should play or could play within the UK's energy system, and how we best chart a development path that goes from the state of play today, i.e. no hydrogen, to lots of hydrogen. And clearly there needs to be a transition between those 2 points, and blending is the first step on that transition. If we look at the history of hydrogen, it isn't a particularly new concept. Cavendish invented it at the back end of the 19th century, and it's been mooted as a fuel of the future for many decades. The The primary reason why hydrogen has yet to penetrate in any meaningful sense within our energy system, even though it's been known and understood for some time, is a very straight commercial issue, that the establishment of the supply chain has been the critical limiting factor, in that the historical model has been based on co-deploying both hydrogen appliances and hydrogen supply at the same time, i.e. establishing a brand new supply chain end-to-end from production through to end use. And that's fantastic on paper, but it's almost impossible to deliver in the real world, because it means that lots of different commercial entities have to all act at the same time, and there's a huge amount of counterfactual risk if one of the parties doesn't act, i.e. you need the entire supply chain to move together at the same point, otherwise the whole system doesn't work. And there are just simply too many commercial risks around that for any private investor to ever want to deal in. And that's been the primary blocker of hydrogen to date. If we compare that to, say, electric vehicles, where electric vehicles were able to penetrate the transportation market because there was an already pre-established electricity supply system that they could tap into. We weren't having to build wind farms at the same point that we're asking people to buy EVs. And that's effectively the learning that the hydrogen industry has taken and then turned that principle into blending. So the point of blending is to enable a non-disruptive amount of hydrogen to be transported within the current system. So we're not looking to change out appliances or change the network to be able to accommodate this change. It all works with the existing asset base, which means all that is required to establish blending is the production itself. And at that point, the commercial chicken and egg of developing the supply chain of hydrogen is then broken, because once the production has been established, you can then start to ramp that up, increase demand, and then you've got a virtuous circle. So that's the kind of strategic purpose of blending, is to break that chicken and egg and make the first step along the hydrogen pathway. Now, blending in itself is a reasonably material measure that we can make. So by providing a blend to all homes in the UK, we would achieve the equivalent carbon savings of removing 2.5 million cars off of the road without anyone noticing, which is a fairly substantial amount of decarbonisation. Put in other terms, it would be the equivalent of fully decarbonising around 1.3 million homes. But that's clearly spread across all homes, and therefore it's a smaller proportion per home. Now on to why we can't do it today. So we can't blend today because the law says we can't, quite simply. There is the Gas Safety Management Regulations that is a secondary piece of legislation that falls under the Health and Safety at Work Act and therefore is governed by the HSE. And within this piece of legislation, it specifically calls out hydrogen and limits its content to 0.1%. Now, the reason for this limit isn't actually a safety concern. It is to make the management of gas quality simpler. So these regulations effectively aligned themselves to the quality of gas that was coming out of the North Sea at the time that the regulations were made, which is in 1996, when all of our gas simply came out of a wellhead within the North Sea. And the way that you can, it is just a simpler management system to limit hydrogen, because then it means that a three-dimensional graph turns into a two-dimensional graph, which is then easier for humans to interpret. And that is quite literally the reason why we have this ban. Now, our gas supply has moved on quite substantially since 1996. We now import about 60% of our natural gas, and clearly as a nation, we are looking to move away from unabated use of natural gas. So this regulation is now clearly not compliant with a net zero system that contains gas as a energy vector. Therefore, it is being challenged through this programme to be able to shift that limit from 0.1% to 20%. To enable that change to take place, we have to build up an argument that demonstrates that the requested gas quality, i.e. natural gas plus 20%, is as safe as natural gas today. That's the challenge that is before us. And if we can meet that challenge, then the HSE will be able to support a change to this regulation, because in very legal speak, we have to be able to demonstrate that those impacted by the change do not have their health and safety prejudiced. And if you can make that argument, then you can change the regulation. The UK government is pretty supportive of blending. So blending at the start of the Hydropoid programme, which started in 2017, was fairly unknown. There was still the ongoing argument of, do we blend, do we do full hydrogen? And then eventually the kind of cogs turned, and people sort of understood that blending is actually a pathway to pure hydrogen, not in competition with it. And since the argument has landed, blending has now really become embedded within government policy. So if we look at the 10-point plan, number 2 on that plan was hydrogen. And in the policy impacts, there's the 5 gigawatts of production, which is often spoken about, but actually the second policy impact is providing a blend to all homes. So that 7% is by energy, which equates to 20% by volume. And then in the target milestones, blending is then called out again, where the government is looking to sanction blending by 2023, which in effect just aligns with our programme timeline, which you can see here. So this is a £23 million programme consolidated into one slide, so you can appreciate that there is a fair amount of simplification within this slide, but hopefully it provides the kind of broadest view of the programme structure. The way that we are trying to change the regulation is by having the HSE review and then us defend that evidence to be able to demonstrate that a blend is as safe as natural gas today. The way that we've done that is by presenting evidence within the context of a trial, because that provides a vehicle for us to engage with the HSE and have them review evidence and deem it to be satisfactory or not, to form the basis of a legal exemption to the regulation itself. The 2 exemptions that we've been able to successfully achieve so far. The first one was for the Keele University trial, which was the first ever exemption that the HSE have granted to the hydrogen limit within GSMR in its history, and that this was granted back in 2019. We then started the trial, which was providing a blend to 100 homes and 30 university buildings for just over a year, and then that trial wrapped up in March of this year. Concurrently to that programme, we then started to develop the safety case and supporting evidence for the first public trial, which is the one that we're currently operating up in Winlayton in the northeast. And this is providing a blend of hydrogen to 668 homes, a church, a school, and a corner shop. And this is out in the real world. So this is on a public gas network. So it's just a normal town. It has all of the variability and inconsistency of the real world, and anyone can be with any supplier. So this really is quite a good example of real world blending. And that trial started on the 4th of August of this year and will run for a year. We are now in the final stage of the programme where we aren't going to run any further trials, but what we are focusing on are the evidence gaps between the evidence that was developed in support of the 2 preceding exemptions and the evidence that is necessary to enable a much broader kind of class approval of blending across the entire gas distribution network. And that evidence gap is what we're now focused on, and we'll be working through that program of technical analysis over the course of the next year, and then looking to engage with the HSE at the back end of next year to then try and defend the evidence and reach an agreed position with the HSE that a blend of hydrogen is as safe as natural gas for every user on the gas distribution network. So just a quick overview of the trials themselves. The Kiel trial was the first use of hydrogen-containing gas in the UK since 1976, when we completed the conversion from town's gas. So it's a relatively historic moment within the energy system. It is the first use of a non-natural gas since our conversion of natural gas or to natural gas. It lasted between October of 19 to March of 21, and for those eagle-eyed of you, you will spot that COVID was therefore quite a major issue that we had to deal with. The fact that the whole world went into lockdown 6 months after we started a trial was not brilliant. It certainly wasn't on our risk register, and did have some minor impacts in terms of resource availability, which is why the trial lasted out to March of this year, because we extended it by a few months just to try to regain some operational time that was lost as a consequence of the lockdowns. The trial overall was incredibly successful, so there were no issues that were identified on the network or the appliances or the meters, the installations, anything really that was attributable to the blend. Clearly, in a live setting, you are going to get faults like boilers breakdown. A boiler will last between 15 and 20 years if you're lucky. So therefore, you will always get a rate of replacement. But all of those kinds of things were all within historical averages, because we mapped them for a few years beforehand to be able to compare. And therefore, we developed a fairly sound evidence base to demonstrate that the rate of failures, if you like, doesn't change as a consequence of introducing a blend. Over the course of the trial, we provided just over 42,000 standard cubic meters of hydrogen, which abated 27 tons of CO2. Now, you can say that in a very excited voice to try and make it sound like a big number. It's not a massive number in terms of overall decarbonisation, but that wasn't really the point of Kiel. The point of Kiel was to demonstrate technical and regulatory feasibility as opposed to trying to decarbonise the UK. And the trial itself provided an incredible, helpful platform to understand how in the real world you would operate hydrogen production and blending in an integrated system against a gas demand that is moving in line with actual consumers, as opposed to sort of abstract spreadsheet analysis, which always has a degree of simplification to it. The live demonstration that we're currently operating is up in Leighton. The picture that you see there is our compound, which is the equivalent of the picture that you saw in the previous slide, where we have both a blending unit and our hydrogen storage. Here we are using hydrogen from Air Products as opposed to hydrogen produced on site by the electrolyzer. So there's a slight difference in the supply strategy that's being applied, but the hydrogen is flowing well, and there have been no issues to date. That statement really applies across the whole infrastructure, in that we've had no issues with the network or the downstream appliances that have been attributable to a blend, and we're now operating at 20% within a process control limit. So the trial so far has basically gone as well as it could have, and we hope that it continues to do so out until the end, which will be Q3 of next year. One of the main bodies of evidence that we are now looking to progress through is the industrial evidence base. Our two trials to date haven't had any industrial users by design. We have kept them very domestically focused, but clearly with a much broader approval, all industrial users on the gas distribution network, which is the overwhelming majority of the UK's industrial base, will see a hydrogen blend, all the way from glass makers to brick makers to bakers. Really every industrial site that you can think of will suddenly see a blend of hydrogen with natural gas as opposed to the natural gas that they are using today. And that clearly poses quite a challenging technical problem for us to try to solve, which is to understand or any potential impacts of a blend on the operation of what is an incredibly diverse range of users. So for domestic users, most appliances are pretty much of a muchness. You know, a boiler within most people's home is pretty much identical. I'm sure the OEMs would challenge that, but broadly speaking, they are very similar, which means you can generalize things quite easily and in quite a robust way. But in a industrial setting, you simply can't do that. So you can't compare a gas engine with a glass furnace because they're just fundamentally different technologies. And therefore, generalization is much harder within the industrial space, which means a much broader evidence base is required with much more bespoke evidence per technology class, and then pulling all of that together to be able to make an argument of the evidence being representative of an incredibly broad user base. But that's one of the challenges that we are working through at the moment, and we have recently successfully delivered the first trial of glass manufacturing, which some may have seen some press releases around, which is where we ran a 5-day trial with Pilkington Glass. So Pilkington invented the float glass process, so is a real kind of world leader of research and innovation. For those of you who don't know, float glass is basically flat glass. It's all the glass that's in your windscreens and your windows and the one you're looking at now on your computer screen. And we ran a 5-day trial where we provided 2 tons of hydrogen each day to their 55 megawatt furnace, and tested both the operational control of the furnace itself as well as the product quality out the back end to ensure that the glass was still safe and still within all of the product quality specifications that it needs to be. And the trial was an overwhelming success. There were no mechanical or instrumentational modifications that were needed within the process to be able to accommodate the change of gas quality, and there was no impact on the quality that meant any of the relevant quality specifications were suddenly non-compliant. So effectively, we demonstrated that you can make compliant glass with the current furnace design, which was a real win. And we're looking to run similar trials with the ceramic industry, the baking industry, which should be quite interesting, where we're making bread, cakes and biscuits next year with a blend, and also making things like bricks and refractories, etc., and doing lots of comparative testing as well as some fairly in-depth conceptual work with OEMs. And that's my generic slide. So if anyone would like to have any questions, please fire away and I'll answer them in the time that we have remaining.
Thanks, Tommy. Yeah, we have a few questions. I'm going to start obliquely with something you did mention, but has also been brought up in the chat, that we did make the change from town gas to natural gas back in the 60s. How does this compare? So in the trial towns, I think what you're saying, to preempt you, sorry, is that as far as the user is concerned, there's no change.
In terms of the domestic user, yes, there will be no changes that are needed. So we've developed a fairly rigorous evidence base that demonstrates that all natural gas appliances dating back to 1976, when the first natural gas appliances were introduced, that all domestic appliances from then until today are capable of safely blending or safely operating on a blend of hydrogen and natural gas, as well as the installation pipework. So yes, for the domestic consumer, there won't be any changes that they will see.
And there's I've seen an advert for at least one boiler as being hydrogen blend ready. Is that a meaningful statement?
It's a relatively meaningful statement. So we've been working very closely with the 4 major boiler manufacturers in the UK. So this is Worcester, Bosch, Baxi, Valent, and Ideal, and we've been working with them really since the start of the program. And it's basically from the evidence that we have generated through the program and through our engagement with the OEMs that they've now reached a kind of public position that their appliances are capable of safely operating with a blend. Now, from a consumer perspective, what it means is that all of your warranties are still valid, which is ultimately where the kind of legal rubber hits the road. So having OEMs publicly committing to this is quite a meaningful step, because there are potential legal consequences of particularly around warranties and the certification of appliances, which is a standardized system. So for them to have sufficient confidence that this change of gas quality doesn't impact the safety or performance of their appliances is quite a meaningful thing, really.
Sure. So one other question that occurs to me around the blended solution is the one of metering. Is that straightforward as well?
What particularly is the question around accuracy or asset integrity?
Well, first of all, assuming that the blend is consistent, can we use the same metering equipment that we have installed already?
So this is fiscal meters that you're talking about, so billing meters within homes.
Essentially the ones that the billing is based on.
Yeah. So that's part of the investigations that we're now undertaking. We are running we are trying to solve that question through two ways. The first question is accurate. So can you still meter the appropriate amount of gas to the relevant standards that it needs to be able to be classified as a billing meter? And they are very stringent accuracy requirements. We are running a accuracy program with NEL. So this is the National Engineering Lab up in Scotland. They effectively own the standards of flow accuracy within the UK. So on the kind of traceability chart for standards, they are the top for the UK, and they're one of the preeminent flow measurement labs in the world. We are running a program with them based on testing a variety of meters, including both diaphragm and ultrasonic, which are the two fiscal meter types that we use in the UK, but also looking at process control as well. So looking at other meter measurement types like Coriolis and Vortex, etc., that aren't used for fiscal accuracy, but are used in process control to confirm that they're accurate as well. That testing is underway. The results so far look incredibly positive, but I wouldn't want to preempt the overall conclusions until we get the research results. And then the second string to that is then the asset integrity work, which is to demonstrate that the components and materials within the meters themselves are suitable to be exposed to a blend, i.e. that they aren't going to fall apart as soon as the blend is exposed to them. And that's work that's been underway. We've made that demonstration twice because we had to be able to justify the trials, but we are looking to then broaden that argument out to a UK representative argument. Yeah, so all of the headwinds look, but we'll wait for the final data to be in.
Yeah, nobody's asked about this, so we don't really need to go into it, but we have been asked. We are aware that we do need to do a bit more materials research on the reaction to hydrogen in the larger network, in the whole supply chain. No, I'm not going to go on about metering much further. Let's cover a little more ground. I think the big question for most people, it's popped up once or twice in the Q&A, etc., is what happens? How do you envisage going beyond 20%? Presumably, you've still got the residual 80%, which is relatively high carbon intensity. How do we start dealing with that?
Yes, good question. So the official answer is that there is no conversion strategy that's been agreed. So all I can give you is my opinion on what I think will happen. I can't see us taking any transitory step between 20 and 100%. The reason for that is that the primary consideration is the point at which you have to change out appliances. So I'm sure that the 20% is probably okay to be pushed a bit more. You know, it's not that at 20.1 everything suddenly falls apart. I'm sure that from a technical perspective, you could probably push it higher. You would need to do a lot of research and basically rerun high deploy at a different blend rate to be able to make the demonstration, but I'm sure technically that it could be made. The real sort of strategic stepping point is when appliances can no longer perform properly with the gas quality that's being delivered to them, i.e. you need new appliances. And that's what the hydrogen ready appliance program is really trying to deliver. So through the High for Heat program, OEMs like Worcester Bosch and Baxi developed hydrogen ready boilers, and the intent behind this is to borrow the strategy that was used for HD ready TVs, where you basically saturate the market with a technology that's future proof. So at the point of transition, it becomes much easier to make that transition, i.e. you aren't having to go around to each home and change out the appliances at the same point that you're trying to change them over to hydrogen. The point is that over the next sort of 10 years or so, the appliances within homes will naturally become hydrogen ready. So you've got a call happening from boiler manufacturers to the government asking for regulation to mandate that hydrogen ready becomes mandatory. Assuming that takes place, then from that point on, one asset cycle past that point, you would expect that the vast majority of homes within the UK would then have hydrogen ready appliances naturally installed in their homes. And therefore the transition point becomes much easier to handle, because you would be looking at maybe changing out one component of a boiler, which you would do as a service, as opposed to changing out the whole installation itself. So that's the kind of critical factor that has to be considered, is how you manage that transition of appliances, in that you wouldn't go to 60% hydrogen that would then need a different appliance, and then 5 years later ask everyone to then buy a new appliance to go to pure hydrogen. You would just do it in one step.
That sounds entirely more manageable than what some people have seemingly envisaged, which is you know, like the conversion from town gas and having to go to every household and at least convert burners and things.
So there would be a level of conversion that would be necessary. You wouldn't just be able to switch the gas over. You need to, but the sort of strategy has been that level of conversion should be no more disruptive than a service today. So most homes in the UK get their boiler gas safe checked each year. At least that's what you should be doing. And the strategy is to say that any conversion that's needed, if you like, should look and feel just like a gas safe check now. So you are maybe changing out a single relatively inexpensive component, and then you've got a hydrogen ready system good to go.
And could you do that on a area, region, community by community basis? So you'd be providing.
Yes. So with.
Yeah. Go on.
Yes, exactly. And the kind of conversion kit, if you like, would be sold at the point of sale. So you aren't having to re-engage with consumers. It's all built into the price. So the gas safe engineer who's going to come to your home in 5 years' time to change out your burner has already been, booked in and paid for at the point where you bought the appliance. So from the consumer's perspective, it's not then a lot of aggro to then re-engage with the conversion process.
Okay. Switching gears slightly, there's a few questions about where we get the hydrogen itself from. I know the government is running a consultation on what could be labelled as low carbon hydrogen. Where's the hydrogen in the High Deploy project coming from, and what's the vision for the future?
So the hydrogen that we've used within the High Deploy program has come from two sources. The first trial, we used a 0.5 megawatt electrolyzer that was designed and built by ITM Power. So we used the green tariff that Keele University have to be able to produce green hydrogen. That's normally the kind of production source that gets the most sort of headlines, if you like. So that was the production technology that we used for the first trial. Due to a number of kind of logistical and engineering constraints, we didn't move the electrolyzer to the second location to then reuse it. What we did instead was to contract with Air Products to have trailered hydrogen delivered. So this is using existing hydrogen supply methods, i.e. SMRs, and then we
what's an SMR?
So it's a steam methane. So a SMR is a steam methane reactor or reformer. This is effectively combining high pressure steam with natural gas to convert it to hydrogen and carbon dioxide.
Okay.
So and then we offset any of the embedded carbon of that hydrogen using approved offsetting methods through tree planting effectively. But it's sort of worth highlighting that the point of High Deploy is not to develop or promote any particular source of hydrogen production. Other programs are looking at that. What we're looking at is at the point that it enters the network down and then downstream to the appliances, how do you ensure that that is a safe system? So as long as the hydrogen is reliable, we really don't matter. Well, it really doesn't matter to our program where it comes from. To be blunt, if we're now looking at the UK system of where will the UK get its hydrogen, we've had the business model that has been put out to consultation by BSI, which is looking to provide the commercial framework for hydrogen production. That would look to provide a support package between the cost of production and some reference price, which is currently taken to be natural gas. And what this enables is then the hydrogen to be sold into the energy market at price parity with natural gas. So no one would pay more, so no consumer would pay more to be able to use hydrogen relative to using natural gas. And then that would be essentially funded through presumably taxation. Now that production method would have to be eligible to receive that support package, would have to be able to meet the low carbon hydrogen standard that's also been put out to consultation. And this is basically to demonstrate that the carbon content of the hydrogen that's being produced is low enough to be able to be classified as a truly low carbon source and therefore be eligible for government support. Now, in reality, it will be that the overwhelming majority of the hydrogen that gets produced, at least for the first sort of 5 to 8 years, will be sort of blue hydrogen, as it's dubbed, i.e. reformation of natural gas combined with carbon capture and storage, simply because the scale at which you can deploy this technology is a few orders of magnitude above anything else, and the cost point is around 1/4 of its alternatives. So it can be built bigger and it's cheaper, and therefore it will win in reality for the first sort of 5 to 8 years, as everyone expects the price of green hydrogen to then become more competitive and therefore see a greater penetration of that technology.
Yeah, it is worth saying that the technology around green hydrogen is developing very rapidly, and the efficiency with which it can be done is always improving. So that is a very realistic target. I've got some fairly specific questions. Apologies if I miss anybody's question out. There are quite a few. Some of them are very technical and definitely of interest, and I think we'll be able to save those and either get back to you later, or at least you'll know that we've taken them on board. The first person who asked a question, I think, is quite interesting. It was Maria, who asked, would it be possible to convert CHP, combined heat and power plant, that's currently using wood chips to use hydrogen? There's a left field question.
Short answer is I don't know. We haven't looked at wood chips CHP for the simple reason that it isn't a natural gas CHP. Our focus is transitioning from natural gas to hydrogen blend. We haven't looked at other alternative baseline technologies. So short answer is I don't know. I'm sure it's technically possible. Whether it's economically feasible is a different question.
Yeah, I mean, presumably anything that involves combustion, you could change, but it would be the more different the material, the fuel, the more difficult the conversion process.
Yes, precisely. Yeah, and yeah. So from a technical standpoint, there really aren't any major issues with doing anything, really. As all engineers probably know, the reason why anything falls down is because you can't afford it.
Yeah. There is one other. I mean, essentially, if we're sticking with gas and combustion, where CO2 is not the only byproduct, is it? So we're still going to get nitrous oxides. I think that's the correct term.
Correct.
So
was that question?
NOxs.
Yep. So all forms of combustion forms NOx. It is a devil that you must dance with, because the NOx ultimately comes from the fact that you're using air, and so you just simply can't get around that fact unless you're willing to separate the nitrogen from air and use pure oxygen. So NOx is an inevitable consequence of all combustion. The question is really, is it to a level that is an issue? Is it a hazardous level? And is it within what is an approved level of NOx? What we've found across all of our testing is that when we've tested every domestic appliance, be it a boiler, cooker, or hob or fire, whatever it is, that the introduction of a hydrogen blend reduces NOx. So all of the appliances built today have to be certified and as being compliant with the relevant emissions standards. So they are all compliant products today in terms of their NOx production, and the introduction of a blend reduces that level even further.
That's good news. Okay, so we're effectively out of time. I'd like to thank everybody who joined, but especially Tommy, who's really been the mainstay here. Is there anything you want to say, Tommy, before we sign off?
Nothing particular. If anyone wishes to get in contact, you can find me on LinkedIn, and I'll be happy to answer any questions.
Yeah, similarly, I'm easy to find. Well, with that, I'll say thank you, everyone, again, and hope they have a good day for the rest of the day.